Hello, let's talk about the deformation which is not temporary. You can see a spring has been loaded with a load, and after the removal, the spring is not restored to its original length. This means the change is now the permanent, and this kind of change or deformation is called the plastic deformation. So removing load is not able to restore the object or the material which is under the test. Now let us take a data for the spring deformation. The spring has been loaded with different loads and the extension has been recorded. Now the data has been drawn on a load extension graph, and we can see the graph shows a straight line and it passes through the origin 0 0. That means when there is no load, there is no extension also. So we can say the load and extension are directly proportional to each other. If we take the gradient or the slope of this graph, we get load divided by the extension. This quantity is very useful for the springs. So this load divided by extension is called the spring constant of the spring, and we can represent it with small k. So we can say F is equal to k multiplied with delta x, or k is F divided by the delta x. The SI unit, of course, F force is measured in Newton and the extension is measured in meter in SI units. So we can say the SI unit for this is the Newton per meter. If we take area under the graph, then we get like a triangle, and the area of the triangle is half base into height, and we get half force into extension. And we know that the force is k multiplied with the delta x, so we can rearrange this as half k delta x square. Force multiplied by extension means the Newton multiplied by meter is the unit for the energy. That means this quantity gives us the energy stored by the spring, and the energy stored by this spring is the elastic potential energy, which can be given as 1 by 2 F delta x or 1 by 2 k delta x square. So the load extension graph gives us the two important quantities. One is the gradient or the slope that gives us the stiffness of the spring, or the spring constant, or the force constant, and the area under the graph gives us the elastic potential energy stored by the spring. Let us consider the data for the three different springs made from three different materials, or like with the different number of turns. We can see we are getting three different graphs. It means the spring constant or stiffness of the springs is different. So for example, we say the extension of 3 centimeter. So for an extension of 3 centimeter in material number 3 needs a force of around 2 Newton. In order to produce the same change for the material number 2, it needs a higher force, and for the same kind of change for the material number 1, it needs even higher value of the force. It means the material number 1, whose stiffness is the largest, needs the largest force among these three materials for the deformation. Therefore, the stiffness of the spring is important for its application, that what actually do you want to do with the spring. So The higher the value of the stiffness means it's difficult to deform the spring. It means the higher value of the force is needed for the small value of the extension. And the material number 3 is easier to deform because its stiffness is small. So stiffness is important while we use the spring. The same data again, and which material has the highest value of the K means the stiffness. So of course the material 1 has the highest gradient or the slope for the load on y-axis and the extension on the x-axis. So we can say that the material 1 has the highest value of the K. So its stiffness is the highest among these three. What does it show? Easier, difficult to deform. So of course the material 1 is the difficult to deform among these three materials. So which is a better spring, low K or a high K? So of course we can't say that the one is the better than the other because it depends upon your application. For example, you are using a spring in a car, so of course you don't want that the car goes down when the four persons sit in the car. So you need spring of the higher value of the stiffness. So when you support want to support a heavy load, and for example, if you are using the spring for the door closer or opener, it means like you don't want the help of the two people to open a door. So of course there you need smaller value of the stiffness for the spring. So it really depends upon the application, where do you actually want to use the spring. Look at this graph. It's not completely a straight line. It shows that the material is elastically deformed till a certain value of the force. So this change is elastic, but after that you can see the graph is not a straight line. So this shows a plastic deformation. So as long as the graph is a straight line, this shows that the material could be restored into its original shape. So there is a limit for that, which we call the proportionality limit or the elastic limit. As a matter of fact, the proportionality limit is little lower than the elastic limit. So elastic limit is the maximum value of the force after which the material is permanently deformed. So if you are using a spring by exceeding the elastic limit, that means your spring is permanently deformed, and you can not actually apply the Hooke's law, which is F is equal to K delta X. So Hooke's law is only applicable when the material is deformed elastically. So most of the application of the springs are in the elastic region, but we should know like where is the elastic limit for a particular spring when we are using in certain application. Let's apply the knowledge gained. We have a spring attached to like a spout, and it hangs with a certain length. We have put a load on it with the mass of 500 gram, and it has been extended by delta x, which is 2 centimeter. We are asked to find what is the force constant or the stiffness of the spring in Newton per meter. So let us consider this mass, and there are two forces acting on it. One is the gravitational force of the earth, and other is the spring force. Because this object is in the state of rest at the moment, it means both the forces are equal in magnitudes. So the load, which is weight, is able to extend it up to certain value, and the spring force is actually don't allow the spring to be more extended. So this force can only extend the spring, so spring allows that much extension only. The spring force is K delta x, and we assume that the elastic limit is not reached. W is equal to mg, so K is mg over delta x. M is the mass, which is 0.5 kilogram, and it's 9.81, and the extension produced is 2 centimeter, 2 into 10 power minus 2, and we get the value of the K as 245 Newton per meter. So its extension, that it needs a 245 Newton of force to produce an extension of 1 meter. How much is the elastic potential energy stored in this spring? So elastic potential energy stored is half K and extension square. So if you use these values, so you get 0.049 joules. And this is the elastic potential energy, which could be changed into the other form of energy when we release the spring. Let us consider another example where a spring has been loaded with a certain load, and this produces an extension of delta x. If the same spring, the identical spring, is added into the system in this way, and the same load has been used, so how much is the extension now? So you can see now the load, which is actually W, is the same, but this load has been shared equally by the two springs. It means every spring actually gains a force than the half of the previous value. It means half of the extension is produced. So every spring is extended now delta x divided with 2. So half of the extension is produced. If you arrange these two identical springs with the same load in this way, so force is experienced by both the springs actually. So both will be extended in the same way, delta x over here, delta x over here. It means the total extension produced is 2 times the delta x. And what about this system? So the W, which is the load, is acted on this, and then it is shared by the two springs. So this produces delta x, and the other two produces delta x over 2. So the total extension produced is 1.5 times the delta x. So by having springs in parallel actually increases their value of the stiffness of the whole system. That's why with the same load the less extension is produced. And using the springs in series, like in the third case, decreases the value of the stiffness. So same load, the whole system, the stiffness of the whole system, the same load is producing more extension. Let's stop here for the plastic deformation.